And now I'll show the solutions. Okay, so the solutions of the first activity about the favorite number and the even numbers, we had time to do it in the tutorial, but this part, the more difficult part, we didn't do it entirely. Well, this is the solution of the first two, and the third one is something that not all of you had time to see it. First, if you have a complex number, for example 3 plus 4j, to get the argument or the face of the complex number, what you need to do is the arctangent of the real part and the imaginary part. And to get the modulus, you need to do the absolute value. And for example here, if I run this code, it will get the argument and the modulus. It's not running very fast. Let me see if I do it again. Let me see something. Why is not running? I'll reload the notebook and do it again. Everything again. Okay. Now it should work. Let's see this one. For some reason it's not running. Let me restart the notebook. Okay. Now it's working. Okay, sorry about that. Okay, if you run the code, you'll get the results in the argument in radians. That's the angle that the complex number does in the real and imaginary plane, the angle between the x-axis and the arrow that represents the complex number. And the modulus is the length of the arrow that represents the complex number in the complex plane. Okay, so here I did a mistake. I'm so sorry about that. That I'll need to explain in the part of the triangular triangle inequality. I'll put the notebook here to write. Here. I also enabled so you can see the pen. Oh, I'm not sure if you can see it or just I can see it, but whatever. What I said in the last TA was that the absolute value or the norm of two complex numbers squared plus this one squared was the triangle inequality, but that's false, and I'm so sorry about that. Now I'll do the real solution. It starts the same. You have two complex numbers, and you multiply the regular complex number and the conjugate to get the modulus squared. And by doing simple algebraic operations, you can see that this is the same as this thing right here. This is the same that I did in the last TA. Whoops, sorry. set here. Then what you need to do is say that this part here is always less or equal than the modulus or the absolute value, because it will get a number, of this thing right here. Okay, this is called well, this is just an inequality. It doesn't have any name. This always will be greater than the real part, because the real part could be positive and negative, and basically if I do the absolute value of the whole complex number with its real part and the imaginary part, is obviously going to be greater than that, the real part. So now I have a inequality here plus 2 times this thing right here. And now I'll use something that is called the Cauchy-Schwarz inequality. Schwarz. I'm not completely sure how to write this. It's a weird name. I think it's written like this. Cauchy Schwarz. I'm not sure if these letters are flipped or not, but whatever. Let me check real. Schwarz. Yes, they are flipped. Sorry, and without the T. Schwarz. Okay, so this inequality, what it says is that you can have this right here that is similar to the inner product, the absolute value of the inner product of two vectors, and this will always be less or equal to the multiplication between the absolute values or the modulus of the complex numbers. Here is for complex numbers, and here this is also satisfied for vectors. So if we do that and replace with the Cauchy-Schwarz inequality, we'll get this thing right here. Here. So now we can factor this, because this is a binomial squared, and we can write it as that, but that is less than this part here, resulting in, if we take the square roots, I'll put it in blue, this here. So this is the correct triangle inequality. And this basically says that if we have two axes and two vectors, this is Z, this is W, I'll use another color, two vectors or complex numbers, it works with both. The summation between them, this length right here, will always be less than the sum of these two. The only case when this is not greater or is just equal is when the thing here is not a triangle and this is collineal in the same line as the summation. That was the mistake I did the last day. I'm so sorry about that. Someone has any doubts about this procedure? Did you see the Cauchy-Schwarz inequality with the professor? This one? Okay, what it means is basically this thing right here, that the lengths of the other sides of the triangle are more than the other one. Yeah, when you have the addition between the two vectors, the length of that is always less than the summation between the lengths. Okay. In any triangle. It's actually true for things that are not triangles, but this is a way to explain it with a triangle. This is true for two vectors in R2 or in Rn. This is a thing that is always satisfied, that the absolute value of the inner product is less or equal than the multiplication of the norms. In the complex numbers, the inner product is the this multiplication here, and the absolute value is the modulus is the norm. This is a very important inequality. So now for the more programming part of this question, you just need to see this. You have two complex numbers. If you see the length of the summation between them is always less than the summation of the lengths. And you can see if you run this cell, it is true. Now, the activity 2 was about drawing triangles with different number of levels. A sub-part of that was to do the alternating pyramid with the number sign and the asterisk. And the other, that it was the more difficult part, was to do a diamond. To do the pyramid, the code is right here, and you get results like this. I will skip this part because you can see it at home. Here you have the solution of the alternating triangle, and for the diamond you have the solution right here. I will upload this, well, it's already uploaded with the solution, so you can see them if you didn't understand something. In the part of computing pi, to solve the summations, you had two summations. The first one here, you can see it, but now you can see it. Okay, so the first one is this one. To generate the numbers, we used a list comprehension, and then you use the summation of that, and that's a very easy way to do a summation. And then, for example, here I plotted the approximation of the Leibniz for pi, with the n as the number of terms that I add. And when you can see here that the yellow line is pi, and the approximation start going near pi when the number of terms increases. For the Euler form of or approximation of pi, you have something similar. And this one is very important. Okay, so I didn't have time to do this one, the Gram-Schmidt process. Basically, the Gram-Schmidt process, what it does is to have three vectors, like these ones, that are not orthogonal, and then by removing the projections between them, it gets three orthonormal vectors. This is very good because with any three vectors, you could get a basis of this space. The procedure mathematically is this one right here. The projection is defined as this operation here, and the first vector is equal to the one you selected as the first one, and then for the second one you remove the projection of this vector to the first one. For the third one, you remove the projection of the third, to the first one and to the second one, and so on. And you get an orthogonal basis here, and to get an orthonormal basis, you need to divide by the norm of the vector. The question here was to define a function that, given 3 vectors in 3D, gave other 3 vectors in 3D that are orthonormal. The solution is this one. The projection can be defined as the dot product between this B and U divided by the dot product of U and U and multiplied by U. I didn't explain it well enough in the last TA. Why is the case of that formula? So I'll explain it again very fast. If you have this vector here called V, and you have this vector here called U, and you want to get the projection, the orthogonal projection, or this vector, this is called the projection to U of the vector V. You basically need to do the following. You need to take the vector V and do the inner product or dot product with the vector U, but the unitary vector U. And then this is the length, and then multiply by the direction, and this is the direction. So this will give you the vector here in blue. And how this formula here corresponds to the one I put in the Gram-Schmidt process is because you change this one, the unitary vector, as this, and then what you get is this, and sorry, squared, because you have 2 unitary vectors, and then you can write this as the inner product of the vector with itself, and then you get the formula of the projection. This one. So now we see at the code, and we have exactly that, the dot product between B and U divided by the dot product between U and itself multiplied by U. And to do the process, the first vector is assigned with the first vector of the collection, then we divide by the norm. The second one, we do the same as the algorithm says, we subtract the projection between the V2 and the first vector, and then for the third one we need to remove 2 projections, and we return then the orthonormal basis with the E's, E1, E2, and E3. If we do that, then we get something like this one. Sorry, I forgot to import something. This is not relevant. That should work. Okay. I'm not sure why it's not showing. Nothing is working now. Let me see if I get the error real quick. Oh, it's a shame. I'm not sure what is not working here. Let me try. The plotting function is not working, not the Gram-Schmidt method. This worked like 2 seconds ago. Let me see if this one is working. No, this one is not working. That's very weird. And this one? Yes, I need to run something before. Then I'm not sure what it is. Let me see if it's this one. Or that one, I don't know. Now it's working. Okay. Okay. So I'll minimize this because it's not relevant for the explanation. So here we have the vectors b1, b2, and b3 that I define as 0.5, 0.2, 0.8, 0.3, doesn't matter. But those are shown here in red. As you can see, they are not orthogonal. And after doing the Gram-Schmidt procedure, we obtain the blue vectors. So we can see here that now all the vectors are orthogonal and also have a length of 1. Therefore, they are orthonormal. And we can see it in 3D how the procedure obtains the vectors. Oh, so I just printing the vectors here. This one is the input and the output. Do you have any doubts about this? Did you understand this procedure or what it's doing?
Yes, I try to work later and then could you give a message to try to working?
I didn't quite understand what you said. Can you repeat it?
Yeah, I I I don't I I didn't the this part. So later I try to work in my computer
Mm-hmm.
and then maybe you to help me with some tips if I can do it.
Yes, obviously. If you have any doubts, you can message me in Canvas or
Yeah.
just ask me here now.
Great, great.
I'll be uploading this anyway. The solutions are already up. And we'll start the tutorial 2. The first thing I want to do is very quickly teach you how to write files because I think it's important. First of all, you need to assign what your file uh, will be called. For example, test.txt to a variable here that it's called file name. In Python 3, this is Python 3, it's recommended to open the files with this with function, or I'm not sure what it's called, but basically you do with open and the file name and write, because we are writing the file, and we open it as a name. For example, here I just used file, and here I just wrote the first 10 natural numbers. by doing file.write, and here I put the string 0, 1, 2, 3, 4 until 9. And this part here, the \n, is the line skip. Basically the enter in your keyboard. When you're writing a file and you do enter and you go to this next line, this is what it does. So for example, here I executed and that created a file called text.txt. To read the files is the same, but you don't put the W. And for example, here I do the same with open file name as file. And the important part here is this. File, it has multiple lines. So to read each line, what you do is for line in file, and this line string, it's what it's in each line of the file. For example, here I'm showing that the line 0 corresponds to 0 and the line skip. That's why the other part of this is at the bottom and not next to it. And like that I can show the first 10 numbers, 10 natural numbers. And Benjamin is asking about NumPy read. You can also do that, but this is the most basic way to do it, to read and write a file. You can do it with NumPy as well. For example, NumPy has a function that is called load txt. Then you can upload directly some txt as a NumPy array, but this is the most basic way to do it. So for example, now, oh no, okay, so I'll teach a little bit how to plot the data. That's something that I didn't do the last tutorial. And then we'll have an activity and we'll test a new method that will do groups of 2 people. Yes, we are 10. No, I'm not sure how the groups will end up, but we'll divide the conference in multiple conferences, and each one can talk between each group to do the activity. So you are not alone now, you can talk between each other. That's a thing that we'll do differently. And now, to plot a function, basically you have 2 parts, the axis and the figure itself. That's 2 main components of a plot in general. And we'll use the package matplotlib. That's what I used also to do the 3D thing that I showed. And for example, here I import the cosine, the cosine, the number pi and line space from NumPy. And for matplotlib, from the model pyplot, I import plot, title, x label, and y label. We already saw in the previous TA that line space of 0 to 2 pi and 100 here will make a vector between 0 and 2 pi with 100 numbers, and then we can call the cosine of x to evaluate the vector x. So for example, here we have the cosine of x. This is to plot just one function. If we also have the sine function and we want to plot them at the same plot, we just do another line with plot, but the y2 variable instead of the y1 that had the cosine, and that automatically puts the plot in the same figure with another color. And for example, to add titles, we do title to functions, and to rename the x, we can put x here, and to rename the y label, we can do that. I'll put it in the same line so you can see the plot below. Now, so you can see now that you have the x label, the y label, and a title for your plot. You can also do subplots if you don't want them at the same figure, sorry, at the same, just in the same square. And you can put one besides another one in any configuration. The configuration is selected here by doing the subplot function. The first number is the amount of plots we want going down. The second is the amounts of plots we want to the right side. And these numbers here is to populate the grid we did with these two numbers. For example, if we do 1 2 1, we'll do 1 plot, 2 plots, and we'll fill the first space of that grid with the, in this case, cosine, and then the second space we'll fill it with sine. I show here also that the third argument of plot, you can select the type of line by doing this. For example, if you do put two lines or two minus signs, you'll get a dashed line. And with this R, you can select the color. For example, R is red, and by doing dash and dot, and also a G, that means green, you'll do a dash and a dot, a dash and a dot, and so on. So you have the plot there. You can also do scatter plots. For example, here I show the sequence of digits of pi: 3 1 4 1 5 9 2 6 5 3 5. Obviously not the infinite number of them, but just a short part of them. And you can do that by using the scatter function. If you are curious of getting sequences of numbers, you can go to this website, the online encyclopedia of integer sequences, and you have basically any sequence of numbers known to man, and you can explore them. And also, what you can do is type your sequence, whatever it is, and it will search all the functions that satisfies that sequence of numbers. It's very interesting. Now, this is in red because it's a little bit more advanced. When you want to do a figure, you can also select the figure size with this, and the DPI, or pixel per inch, or the resolution or the quality of your image can be selected there. Usually for publications, that 300 is good enough. So with 300, you're all set with the DPIs, and this is only the size of the figure. So for example, here I plot the same cosine, but wider and also in a better resolution. And now if you want to save that plot, you use the save fig function, and you do that, and you have already saved the myfigure.png file. Okay, so now is the first activity. I'll try to split the groups. Okay, so let's try to do 3 rooms. Okay. Okay, so do you still listen to me? Are you hearing my voice now? I'm not sure. I'm not sure how it works for you, but basically, I splitted the conference in 3 rooms, and now you can talk with each other to do the exercise. And can someone confirm if someone is okay? Hello? Did, did you get that I split the conference and you can work now in groups? Okay, just checking. I'll go to the other room. Okay. Are you listening me? Did you get that I split the conference so you can work in groups to do the activity? You can do the activity the same way as the last TA, where you open the collab as I don't remember exactly the option, but you open it as a copy and start working. Can someone confirm that? Did you understand the solutions? Or sorry, the instructions? Okay. Yeah, well, you have 15 minutes now to talk with each other and try to do the activity. This is not a very difficult activity. It's for you to work with each other and make friends. Okay, so let's start talking, and you can share your screen also between each other and show your progress. I'll go to the other room. See ya. Okay, did you get the instructions? Okay, so did you get the instructions? Okay, did you get the instructions that you can work together? You can do the same as before by opening the Colab notebook, and you can, for example, share the screen and start working together to try to solve this activity. That's the idea, that you talk with each other. This is an experiment. We'll see if it works. I'll go to the first room now.
No, me tira error. ¿Te tira error? Sí, el que aparece ahí, me da como error. Pero tengo error en el post txt, no me encuentro.
You need to run that cell to do the activity. Yes, you need to run that cell first, and then yes. Oh, no, file, no. So put cancel, then file, file. No, file, yes, file, and you need to where is it? Edit. No, edit. There was an option called open as playground or something like that. Oh, he already did. Oh, so just run it then. Just run the cell and put run anyway. That should generate the files.
Yeah, I put the same and it doesn't work.
Let me see what it says. Oh, but you need to run the previous one, the one that defines y1. the the subplots. No. No, plotting multiple functions. Oh yeah, subplots. Yeah, you need to run that one first.
Oh, and then run.
Yeah, and now you need to run that one. Let's try again. Now it's okay.
Okay, thank you.
Okay, I'll go to the second room. Hello? Hello? Did you get that you need to run the subplot cell first to generate the files? There's a cell called subplots that defines the variable y1 and y2. So you yes, you need to run that one first, and then you can run the cell that creates the txt files. Yes. Share your screen so everyone can see what you're doing and you can talk. It's a little bit easier. The other groups are doing that. Okay, so I hope I was helpful. I'll go to the third room.
Entonces, y no puedo compartir porque el drive no puedo dar. Sí, bueno, voy a dar, sí puedo. Pero ahí está, mira, eso fue lo que yo hice. No sé si se ve bien. Yo lo puedo ver. A ver si puedo. Ya. Ahí está el. Ya, ese es el primero. La verdad no sé. Nada. Ya, pero si queréis por último anda explicándonos lo que hiciste y lo hacemos en una pantalla compartida nosotros. Ya, eso hagamos. ¿Pinta? Sí, ya. Me parece. Ya, le digo, sigue compartiendo y lo hacemos. Diego, comparte, mira. Abre...
Acá lo dice que control más puede agrandar la letra del computador.
Ah, ya.
How's everything here? You need help? Okay. But did you run the subplot cell? Okay, so you now have already generated the txt files. I suggest you to do another cell with the plus código that says there and start working in a new cell. Or actually, I think I put a free cell down there, a little bit more there in the hidden cells. That one. Okay, so I'll explain that later. Okay, I'm not sure if you have you can contact me via chat, but if you can, try to do it if you have troubles. I'll see how the others are doing.
Ahí está. Es codificado. Frente arriba. O no, da lo mismo. Da lo mismo. Ahí mira, en la esquina aparece un símbolo de... Ya. Y ahí me tira error. Mira, dale... correcto. Pero según yo, tú lo de la ruta, ¿no?
Me está pasando exactamente lo mismo que antes, como que al final corre, no me tira ningún error, pero tampoco se me genera algún...
Pero, a ver, pon arriba, te muestro el gráfico arriba, porque si estáis generando, ya ponle play ahora, al de abajo.
You can see if the files are correctly created by clicking the folder icon at the left. That folder at the more left, lefter, there. No, the last one, that one. There they are. So you already created the files. Now you need to read them. Yeah, you can work if the files were there already. You don't need to do anything. They are already created there. Oh, that's another thing. Yep. You can see there that those are the files you created. And now you need to read them. Okay, I'll change to the other group.
Perdón. Que yo también sigo en pregrado, pero estoy entrando al magíster de también de ingeniería y también por el lado de bioministro.
Did you... sorry, did you finish the activity? Yeah? Okay. So you can try the next one. Yes. That's the difficult one. No. That was for the first activity that is called read and plot. Yeah, it was a free space to do the first activity. Yeah, but yes. Okay, I'll go to the other. For example, Rocio, are you getting how the things are done? Yes. Nice. Nice. Okay. Are you liking this modality of doing groups? Or you prefer to work alone? Is it? Yes? Yeah, I'll take that in consideration. Yeah, it's an experiment, so I'm glad you liked it. I'll change to other group. See ya.
matplot min.
Esto es de acá.
¿O no?
Sí. No, sí, se habría que ocupar esto. Lo que pasa es que estaba viendo cómo colocar, cómo leer para que al final me tome la información del TXT.
Ah, perfecto.
Entonces, por ejemplo, después hay que generar algo de este estilo, donde tu I1 va a ser tu coseno y tu I2 va a ser tu seno, pero que da la información de acá.
Ya, perfecto.
Y por otro lado, el TXT es 006.5, 006.5, ya son exactamente lo mismo. Oh, ya
No, yo quería seguir jugando. Esto es chino para mí.
no, pero se aprende.
Pero a bruta hay que aprender. Ustedes no están entendiendo que estoy volviendo a estudiar. Yo no tuve cálculo. Pero tampoco, mira, estoy leyéndome el Stuart por primera vez en mi vida.
Ya, pero lo vemos. Pero ahí podemos.
Hello. Hello. Okay, we are waiting for the other people. They must be here in 1 minute. Okay, so everyone is here.
Question, Carlos?
Yes.
How do you do to make the function explanation appear in the screen while you are writing the code?
Oh, this is a Jupyter notebook, the same as the one you have, exactly the same one, but I'm showing them as a slideshow. That's the only difference. So here, for example, I have a markdown cell that you can create by creating a markdown cell with the plus icon that you have in the notebook. And to do the, for example, the code explanation, I just put a code cell, and this is the same as the one you have, but it's displayed in a different way.
No, but I mean, when you are in Jupyter,
Mm-hmm.
and you want to know the parameters that a function has or the utility that it has,
Okay.
and you want to open a window, an explanation.
Okay. The documentation. For example, I have here the enumerate function. I press Shift and Tab, and that opens a window here, and I can select the plus, and I have the explanation. Yes, and I have the explanation and what the input means. For example, let's choose another tab. For example, here the plot function plot y versus x as lines or markers, and I put the plus icon, and I have the explanation of each input. And here you have the explanation, and also usually you have examples. For example, I have an example here. So if you have doubts, Shift and Tab. The more advanced activity was the dragon curve. I will not do it right now, but that's for you. You need to look up this video. It's a very good video. And we'll continue. Now, for the matrix manipulation, we already talked about the matrix and vector multiplication in the previous tutorial, but I'll be more specific now. I'm sure that not all of you remember or know what the matrix vector multiplication is. So here, for example, I have a vector x and a matrix A that when you multiply them, you obtain a vector v. As you can see, the matrix A has dimensions m and n. That means that it has m rows and n columns. The vector x is n times 1 because it has n rows and 1 column. And the vector here, b, it has m rows and 1 column. When you do a matrix vector multiplication, what you do, for example here, to get the blue value of the b vector, you multiply the second, in this case, the second row of the matrix with the vector and add them up. Mathematically, this is expressed as summatory or a summation, in which each element of the row is multiplied by the corresponding element of the vector x, obtaining the vector v at the position I. To obtain the vector v at position I plus 1, do the same multiplication but with the I plus 1 row of the matrix A. Now, how do you do that in Python? You, for example, can create an array. Here I created a matrix 1, 2, 3, and 4, and a vector x. And to multiply them, you can do the dot product, or if you have Python superior to the version 3.5, that's our case, you can do the dot product with the with this symbol here, the @ symbol, and it does basically the same. So this is an easier way to do the dot product in Python superior to 3.5. And as you can see, 7 here is equal to this row multiplied by the vector 1, 3. That means 1 times 1, 1, and 3 times 2, 6. 6 plus 1 is equal to 7. And for the second row, you have 3 and 4. The 3 is multiplied by 1, and the 3 here is multiplied by 4. So you obtain 12 plus 3 equals 15. So that's correct. For the matrix product, you have instead of a vector here, another matrix, and the result will also be a matrix. And to get this blue square, you multiply the row 1, for example, of the first matrix and the column 1 of the second matrix. This is written mathematically as this. You cannot see the full line, but basically for every position of the matrix C, you can obtain the value of that position multiplying a row and a column. And for example, if you want the C2 value, you multiply the first row here and the second row there. If you want the third, the first row here and the third column here. And you add them up. And so on. If you want to do that in Python, you do the same. You can do the dot product or use the @ symbol. This only works for Python superior to 3.5, but is very easy to do. Now, an example of operations between matrix. I'm not sure why it's showing that way, but basically here we have an example that is called the QR decomposition. What it does is to have, for example, a matrix A in which the columns A1, A2, and A3 define the matrix, and you want to express this matrix as a multiplication of another matrix here, Q, that has vectors E1, E2, E3 that are orthonormal, and an upper diagonal matrix, that is this one, the R matrix. One cool thing about this matrix that is done by concatenating orthogonal or orthonormal actually vectors is that the matrix, that's the thing showed here, that the matrix times the transpose of the matrix is equal to the identity. What it means is that they are orthonormal. You can also do it in the opposite order. This is called, when a matrix satisfies this property here, is called a unitary matrix. And the unitary matrix are the ones that has columns that are orthonormal. But I have a question for you now, because you can get the QR decomposition using mechanical operations between the columns of A to get orthonormal vectors E. Does that sound familiar for you? Where did you see about how to get an orthonormal collection of vectors from a non-orthonormal collection? Gram-Schmidt. This is very similar to Gram-Schmidt, the procedure we already seen, and that's no coincidence, because if you do the QR decomposition of a matrix A here, that is the same it's the same vectors as the one we did before, b1, b2, and b3, but I concatenate them as they are the columns of the matrix. For example, the first vector v1 is the first column of the matrix, the second vector v2 is the second column of the matrix, and the third vector v3 is the third column of the matrix. So you have that matrix A, and I want to do the QR decomposition with this command. And what I obtain is that previously I had these red arrows. The red arrows. Sorry, I need to run another line. But now should be working. Okay. Well, I'm not sure why it went down there, but basically you had the red arrows that you obtained with the Gram-Schmidt procedure, and here this arrow there is the same in the QR decomposition when you compare it with the Gram-Schmidt procedure, and the other vectors, as you can see, are basically the same between the QR decomposition and the Gram-Schmidt procedure. The only thing that changes is the direction, but that's basically multiplied by a scalar. So what we obtain by looking at this is that when you do the QR decomposition of a matrix that is done with a lot of vectors as columns, you basically what you get is the Gram-Schmidt procedure automatically. You don't need to do anything. The red arrows here are the ones we obtain with our function, and the blue ones are with the QR decomposition. So it's very surprising that both are the same. Something is happening here. Let me close this because it's not rendering correctly. Let me see if now it's okay. Okay, so another thing that's very important is that the matrix vector product can also be interpreted as a linear combination between the columns of the matrix and the vector x. For example, here you can write A times x, the matrix A, and a vector x as the first element of x times the first column of A, until the last column of A times the last value of x. This thing right here, we already saw in class that this is a linear combination of the columns of A, because x is multiplying the vectors and then you add them. Why is this important? Next. I'm not sure why it's... Okay. So for example, here, in red, I have the vectors that are the same as the columns of a matrix A. And in blue, I have my other vector x, and when I multiply A times x, I'm basically multiplying the red part with the blue part, and what I'm getting is the green vector. as you can see, in this case, the vector x is 2, 0, 0. But as you can see, the green result is in the same direction that the, for example, could be the first column of A. What happens if I do the same, but the x now has a 2 in the y direction? The green result goes in the same direction as the second column of A. And if I do it in the third one, you can see that in the third dimension, x pointing upwards, you get the green vector here that is in the same direction as the third column of A. And obviously, if you do a combination of, for example, the x and the z component, you have a linear combination of the columns. The resulting vector in green is a linear combination of the first vector here that represents the first column of the matrix A and the, in this case, the third, I can show it in this plane, the third column right there. So the green is 1 times the first and 2 times this one. You can see it right there. Let me see. Okay, you can see it right there. The green is 1 times this and 2 times that. So it's a linear combination of the columns of A. Any doubts about this? Did you get what what I'm trying to show here? That the green is 2 times this one and 2 times this one and 1 time this one? Nobody's talking, so yes? Did everyone get what I'm saying? I'll ask in negative. Someone did not get why a matrix vector multiplication is a linear combination of the columns? Okay. Yeah. Mm-hmm. You need to run the cells in order, so probably that's why the error is there. But you should see the same plot and play. You can play with it. A recommended video to understand how the matrix vector multiplication is equal to a linear transformation is this one here. I strongly recommend you to see it. It's the same that I already showed, but much prettier. Mine is nothing compared to this video, and you can get intuition about the mathematics that are behind the linear transformations. Okay. Yes?
Doesn't matter if you don't give a numerical number to A.
Let me see. This one? No, I already did. I did assign a numerical value of A in the previous cell. So here. Sorry, it was my mistake. I should put it again. It's not necessary, but for understanding purposes, it's better if it's twice there. Yes, you can define it there. and b1, b2, and b3 are the same vectors that we did in the Gram-Schmidt procedure, just because they are already defined. Okay, so the next part is, why is this important? Because a lot of physical scenarios or things in life can be modeled as a matrix vector multiplication, and that's part of the modeling. And I'm sure a lot of you will need to do some modeling at some part of your thesis, so it's important to have a problem and translate it to the math behind it. And specifically, if it's a linear problem, like the ones I'll show here, it will be direct. Okay, so the first example is the example of the magic square. Has anyone has anyone seen what a magic square is, or before, or is the first time you hear about the magic square? First time, okay. A magic square is like a Sudoku type of puzzle in which you have, for example, here 3 by 3 slots, and you try to fill the numbers so each row adds to the same value. Actually, the goal here is to fill with all the numbers between 1 and 9, for example, because it's a 3 by 3 square. You need to use all the numbers until 9, and when you do that, you need to do it in a way so it adds to 15 in this case, in each column and in the diagonals as well. So how do you translate that as a matrix vector product? I'll change to the document here I can write. So basically we had, I'll use the same numbers. No, I'll use A, B, no, x1, x2, x3, x4, x5, x6, okay, a lot of numbers, x9. And you basically need that this row here, or x1 plus x2 plus x3, is equal to 15. This row here, that is x4 plus x5 plus this, is equal to 15, and so on. x7 plus x8 plus x9 equal to 15. You also want that these things here, x3 plus x6 plus x9, this is an x, 15, and so on. I will not write all the equations, but basically you'll have 1, 2, 3, 4, 5, 6, 7, and 8 equations. So you have 8 equations. And how many unknowns you have? Or variables? You have 1, 2, 3, 4, 5, 6, 8, well, 9. You have 9 variables. What does that mean? That basically you have a matrix A, yeah, and you have a vector X, and you want that to be 15, 15, 15, 15, 15. How many 15s? 8. 8 equations, so 8 15s. And you'll have 9 variables, and this matrix here will be 8 times 9, right? So it will be 8 and 9. And here, you basically will have something like this. I'll just write the first equation. For example, you have x1, x9. And the first equation, or this one, I'll write it here, is 1, because you have 1 times the first variable, 1 time the second, and 1 time the third, and a lot of zeros. For the second one, I write it here, and you have basically 0, 0, 0, 1, 1, 1, 0, 0, I'll rewrite this so it makes more sense. 1, 1, 1, 0, 0, 0, 0, and that's it. So now we can write all the numbers there. There. And for the third one, obviously, you'll have the third row 0, 0, 0, 0, 0, 0, 1, 1, 1. And you can do the same for all the equalities. But someone has already figured out that basically you have 9 variables and 8 equations, so that's unsolvable. You cannot solve this. That's called an undetermined determined problem. And that's because the number of equations, m, and the number of variables, n, are with this relationship. That means that you have more unknowns than you have equations. That's impossible to solve. And you have a lot of cases when m is equal to 1. You have when m is less than n and more than n. M being the number of equations, and here being the number of variables. When they are the same, it could be a determined problem. Here is you have more variables than equations, so it's undetermined, so you cannot have a solution, or you have infinite solutions. You have one solution here, infinite. I'll just put the infinite sign. Infinite. No, here no, sorry. And here, I'm not sure how it's in English, but it's the opposite of undetermined. Is over. Okay, so basically you don't have a solution here, you have infinite here, and you have one solution there. Yes?
When we have an undetermined solution, even though we can't, we have more than one solution, can one find, for example, like the space in which these solutions are?
Yes.
That's one question. And the other question is, like for this case, I don't think we can have infinite solutions because there isn't like an infinite amount of combinations of numbers from 1 to 9. How can you have infinite solutions?
No, in this case, there you have a restriction to a problem. If you only have the problem a equals to b, you don't have a solution. But you also have that this is subject to that the variables here, x of a are can only be between 1 and 9. So that's why you don't have infinite in this particular case. So the restriction reduces the space and solves the infinite solution problem. And now that's something there. Whoops. Sorry, now. Another problem that could be modeled as a linear combination or operation between a matrix and a vector is the computerized tomography problem. The computerized tomography problem is the one that uses X-rays to reconstruct a 3D volume. For example, here is the head of a patient, and you basically have X-rays, these red lines, going through, and in each angle you'll have a different X-ray profile or shadow. This is the thing showed here. But this is not that different from the magic square, because basically if you put a body as a matrix, you have that this ray here is just adding up all the things that crosses and resulting in this value. And when you vary the angle, you start generating this thing here. In each angle, I'll have a projection that is just a summation of the things inside the body. And finally, what you get is what it's called a sinogram. And well, in reality, people obtain a sinogram from the CT and then solve a problem similar to the one in the magic square. Try to solve the problem A equals X equals to V, and obtain the head of a patient in this case. I think you have classes now, so we'll end up here. But that thing, one thing that you should know about is that you can obtain the columns of a matrix A by, for example, if you don't know what the impulse response is a little bit problematic, but very quickly, so before you leave, if you have a very complex system that is represented by the matrix A, and you have the columns here, and you want to know how the columns are, and this represents your system, what I try to do is see the impulse response. The impulse response is basically just put a 1 in one place and 0 in all the others. And what you can see here is by doing the matrix vector multiplication, you'll get the first column. If you do 0, 1, 0, da da da, A, you'll get the second one, and so on. So if you have here zeros, a 1 in the ith position, and zeros, multiplied by the matrix A, you'll get the ith column. So that could be very useful to define the matrix that represents a system if you don't know the exact vectors. For example, in this case of the computerized tomography, what it means to put a 1 and zeros is to have a body that is just a 1 in this point. Then, for the second part, this is the first case, for this one is to have only a 1 there. For this one is to have a 1 there. And you basically start sampling a lot of points by putting only a 1 and 0, and you'll get the if you put that in your system, for example, if you put that in your CT that is represented by this tube, you'll get something that is the impulse response and that's equal to a column of A. So I want to end up with that, and the last activity it will be for home, and basically is to try to solve a Sudoku, but very small. Sorry. The last activity is to solve a Sudoku, but a small one, by representing the problem as a linear operator over a vector x, and try to solve it with your programming skills. That's it. Okay. That will be all for today. I strongly suggest you to try to do the activity too. We didn't have time today, but same as this tutorial, I'll be showing the solutions in the next TA. Any final doubts or comments? Something that you want to be explained better the next TA or something like that to take in consideration? Because you'll have the first homework published the 31st of this month, I think. So all of this here will be very useful for your homework. Any final comments? No? Yeah, I think it's next week. Let me check because I have the calendar here. Let me see. The next TA is the is the 31st of March, and it will be the next Tuesday, and it will be about solving linear systems, introduction to random number generation, and for example what a normal distribution is, and something about noise. That is something that always appears when we try to solve systems. Any other comment or thing to say? If not, we just finish the TA. Someone wants to try to solve the activity now with me? I don't know, in 15 minutes. I'm sure that some of you have classes now, but if you don't, we can do the activity. Yes? You can raise the hand in the chat if you want to do the activity. We'll do it in the same modality as before with the groups, and I'll be helping. Okay, if someone don't want to see the solution or try to do it, you can leave now, and this will still be recorded, and so there's no problem for you to go to another class. Okay. Bye. Okay, so the people that want to solve the activity, just stay here, and I'll do the groups. No problem. Okay, so everyone here wants to do the activity, or Carlos? Yeah. Diego? Yes? Okay, so we'll do it together. I'll make 2 groups now, because I like the idea to make groups. I'll do just 2 rooms because we are less people now. Okay. Hi. If you want, you can talk in Spanish. I'm the only one that needs to talk in English. Yes.
Carlos, do you speak Spanish?
Yes.
Genial. Ya. Bien.
¿Compartís pantalla tú o yo?
Dale tú.
Yo no lo tengo abierto. ¿Lo tenés tú abierto por si acaso?
A ver. ¿Qué tal si aparece? Sí. Ya, yo comparto pantalla.
Ya.
¿Bien, bien?
Sí, perfecto.
Ya. Voy a borrar este segundo y está. Ya, entonces, el número entre 1 y 4 y cada columna de 1 por 2.
Y ahí todos suman 10.
Todos
Son
suman
4,
pero
4, 8 y 2 más. 10.
Pero se supone que cada columna, cada fila y cada bloque 2 por 2, supongo que serán estas, pues. Un bloque, dos bloques, tres bloques, cuatro bloques. Ya.
Entonces ya perfecto.
Sí, son 2 ocasiones. Y por otro lado.
Y no. Y 8 en común ya.
Sí, 8,
Están en
7, 7.
7, como que en la arriba faltan.
Son 7 infinitas.
Eso está, de hecho, está sobredeterminado.
Entonces, las expresar este problema.
Taking into account that usually when you have, for example, more equations than variables is overdetermined, but those equations could be linearly dependent. So the rank of the matrix could be less or more. The thing you need to see is actually how many of them are linearly independent. So if you have 20 equations, the useful information there could be equivalent to only 10 equations. Mm-hmm. Yes, you can program it in Python. No, not that much. It's just you need to make the matrix A and the vector V and just solve the system and see what you get. Because and see how it differs by you solving it by hand. That problem is very easy to solve by hand. Try to solve it by hand and then see what the solution of the system is.
What I'm asking is, can you, is there some way to immediately reduce the matrix A into its...
Oh, okay, the rank. You want to do the Gaussian elimination.
I want to see exactly from A how many of them are LZ, and also I want to see how the vector X is, what it becomes, then you get exclusively...
Yes. Yes, you can solve the problem by doing the minimum square solution, and to get the nearly independent part of the matrix A, you need to do the rank of the matrix. You need to Google the function, but that's a very standard function. The rank of a matrix. The rank is the number of linearly independent columns. Yeah, it should be short. Is a lot of numbers are already filled up, so that part doesn't add information. Okay, I'll go to the other room. Hello, how are you?
Hello. Hello. Hi.
Yeah, you can speak in Spanish, but I need to speak in English.
Ya, entiendo.
Yes. So
Estoy como anotando más o menos las ecuaciones del sistema. José, ¿estás
perfect.
cachando más o menos por dónde está dando todo, cierto?
Sí, sí, lo estoy cachando. Sí, te estoy siguiendo acá con mi papel.
Yeah.
Más 2 más 3 igual a 10. ¿Ya? Y bueno, hay 4 ecuaciones más.
Sí, la de los cuadrados, sí.
Entonces, si uno lo lleva esto a formato matricial, ¿ya? Sería, por ejemplo, una forma de ordenarlo sería decir que voy a hacer un lápiz negro, la ecuación 1 es el 1 más el 2, 1 int, y ninguna otra signo, entonces 0, 0, 0, 0 y 0. La ecuación, esta es la ecuación 1, 2,
Bueno, ya no sabía cómo manejar el 6 y el 1. Entonces, ya.
¿cierto? Entonces, en la ecuación 2 tenemos que es 0, 0, 1, 0, 0, 1, y una variable 0, 0, 0. ¿Ya? En la ecuación 3 tenemos oye, está buena esa. ¿Cómo lo hiciste con anotar?
Sí.
Ah, está
¿Dónde está eso?
Arriba donde dice usted está viendo la pantalla de Diego, con interacciones, y
acá
dice
sale.
Ah, buena.
Oh, está bien, está bueno.
La filete.
Ya, a ver,
Ya,
entonces sería, ya era 1, 2, 3, 4, 5, 6, 7.
sí, hagámoslo así.
Sorry, I did something. I I wanted to try the thing. I'm not sure how to remove it, so it'll stay there.
ya, entonces ¿cómo hacer? ¿Así?
2, 3, 4, 5, 6, 7.
Ya, perfecto.
Entonces, siguiendo eso, ya, si alguien me puede ir dictando.
Ya, entonces sería 1, 2.
No, lo que pasa es que hay que reescribirlo para que te quede.
Esto por x1, x2, x3, x4, x5, x6, x7. Y eso es igual a... Y ahora acá está el problema, porque claro, tienes que restarle 4 al 10, es 6, estos son 5, 6, 4, estos son 4, 6, estos son 1, 3, 4, 6, creo que no tengo una cocina, 6 también, 6, 6, 6, y no puse esta ecuación de acá, no la puse en ningún lado para que no se me termine el problema. Y bueno, de acá resolverlo. El problema de esto es que si uno no le dice al programa como con un for detallado, ¿ya? Puede que que ponga en vez de valores como 1, 2, 3 o 4, ponga valores del tipo 28 y menos 27.
Ya.
¿Cachai? como ves, yo sí programo algo.
Profesor, o sea, de mi parte.
Pero no, solamente bueno, acá uno puede importar núcleo por núcleo. Esa es otra forma de importar las cosas.
Esa la cachaba,
Ya, perfecto. Y esto lo tengo que guardar en algún lado.
Do you hear me? No?
Normalmente dependiendo. Agreguémosle todas las otras cosas. ¿Cachaste lo que pasó?
Sí, se me salió la circular, era porque son lineales de núcleo dependientes, como cuando éramos linealmente de núcleos vectores.
Carlos,
Hello.
¿puedes mover mi mouse?
Awesome. I just wanted to test the remote control thing. You can do a lot of stuff. Pretty useful to know.
Sí, que se puede. Eso sí me tenía que ver un permiso
Mm.
antes de realizarlo. Pero es muy bueno saberlo.
So now you know.
Sé que hay más ecuaciones que hay,
Mhm.
pero decidí poner shooter por una cosa de que un sistema de shooter ecuaciones o un shooter técnica me parecía lo más sensato.
Yes. Probably the ones you removed are linearly dependent anyway,
Sí,
so it doesn't matter.
así que hay que agregarlo.
Try to solve it.
¿Ah?
Solve it.
Yo lo intenté resolver y me salió que la matriz era singular.
That means that the matrix A has linearly dependent columns, yes. You can see which one by doing the ref, that means the Gaussian elimination, and also you can do it by using the rank function. Not sure. No, I need to do it again. There.
Ok.
Sorry.
Si muevo mi mouse, ¿pierdes el control o no? Oh.
I'm the boss.
Bueno, agreguemos que ya tenemos escrita el lado. Que sería la 0 con
Dice que array no está defined, baja. Array is not defined.
a lo mejor tenía que generar otro antes que no lo generé acá. Puede ser algún código que esté incluyendo la array. Acá.
From NumPy import array.
Ah, qué bueno. Y te tira el tiro al error que te sale. Ya. Entonces. Ahora sí. Ah, pero no le puse nada. Ah, punto.
It's with the at symbol. Yes.
But the add is multiplication of the matrix, or not?
Yes.
But we can't solve the system.
Ah, okay. So you need to find a function to solve the system. You can look up how to solve a linear system with the minimum least square method. You can look it up in Google or something. Whoops. Well, you can continue with that function. Christine, are you there?
Sí.
Are you doing it also?
No, I'm watching how
Okay. But are you understanding so far what he's doing?
yes,
Okay.
also, but kind of.
Okay. Well, try to understand, and if you don't understand something, you can ask your teammates or me. I'll be looking the other group. You can speak in Spanish if you want.
Sí, es que estoy estudiando, yo no tuve cálculo, entonces estoy estudiando cálculo, todo nuevo.
Mm. If y- if you if you want a good source to study the basics, use the Stuart book.
Sí, me estoy leyendo eso.
Yeah, for Introduction to Calculus and Calculus 1.
Sí, me leí la introducción y ahora estoy en cálculo 1.
Nice.
Pero para entender esta materia bien no está ahí todavía cálculo, pues. Tienes que irte al libro de álgebra lineal.
But the Stuart has linear algebra. I think the one with the precalculus or calculus 1, it has also about linear algebra.
No, pero tiene solamente resolución de sistemas de ecuaciones, no tiene más que eso. Por ejemplo, transformación lineal o bases vectoriales, ese tipo de cosas no lo tienen los cursos.
No.
No, eso estaba mirando, no lo tiene.
Sí, mándame. Yo la otra vez sé que te había dado tu.
Tengo tu número.
Ya, mira, mándame tu correo porque yo tengo un libro bueno para niños.
Ya.
Que es súper amigable y lo ocupan para el curso en la universidad.
Ya, bueno. Ya, bacán. Gracias.
Nice.
Sí, estoy leyendo.
Todo esto dentro de la legalidad de.
I didn't hear anything. Okay, keep working.
Alguien que es más de ciencia, de la salud, es distinto, es otra visión.
Mm. uh, well, I'll be looking the other room.
Okay, thanks.
And did you solve the system?
Carlos.
No me gusta PayPal.
A mí me carga, la cosa es que claro, cuando puse esto en Google buscándolo, ocupa syntax.
It doesn't matter. Use the NumPy implementation. It's a very small matrix. There will be no difference.
La cosa es que no encontré código de...
That's different. Yeah, I think you're correct. There's no implementation in NumPy.
Pues claro, ahora me dice que los últimos dos elementos de la matriz no son cuadrados.
Ah. But it doesn't matter if the matrix is not squared.
Esto como que me causa duda de cuál es el problema del programa.
Another way is you can try to use the pseudo inverse. NumPy? No, the pseudo inverse. In NumPy is p inv. Yes. Inv. That one. That one. And you multiply that by b.
Y esto sería multiplicarlo por la derecha, entonces también lo voy a poner comentario y lo corremos acá a m ya es la inversa, así que a por b. Vaya, me dio una matriz.
The solution should have that vector should have the same number of elements as the unknowns. But I'm not sure why you have a matrix. No, that's incorrect. Oh, I know why. It's because you use the just the multiplication. That's component wise. You need to do the at symbol. In Spanish es arroba. A arroba B. That does the same as dot. No, it's the same, but one is shorter. You see? Yeah. That is not in lin alg. Arroba. But you got a solution. Probably it's because your matrix is incorrect. But you got a solution. The pseudo inverse applies even if the matrix is not a square matrix.
Perdón, Jorge, como que te dejé de lado un segundo. Lo que estoy haciendo ahora es agregar las funciones que me faltan de acá, poniéndola a la de este cuadrado, este cuadrado, este cuadrado, este cuadrado, decía ayúdame. Me imagino que algo así. A veces como que se me olvida explicar lo que estoy haciendo.
That's the last one.
Y esta es la última línea, que sería el 0,0,0,0.
Now the vector v.
Y me falta arreglar el b, que sería la primera que le agregamos en 6, luego en 8, metiéndolo acá, 2, 4, bien, un 4 acá bien, el 3 acá bien, el 4 bien, y la respuesta.
Congratulations! Now you know the power of math. I'll go to another group, but you already finished. No, actually, I'll join the groups. I'll finish the thing. The other one, you'll show the solution. Hi. Another person already finished, another group actually. So he'll show the solutions. Benjamin, please show your solution and explain it a little bit. You can explain it in Spanish if you want. But you are mute. No.
First, I import NumPy in the
Mm-hmm.
I make the matrix with all the equations. First, with also I make the system. I call the variables x1, x2, x3 to xn. Yeah. And make 12 different equations. One for each row, one for each column, and one for each square. Yeah. That I represent you here in matrix A with 1 and 0, and the rest of the elements like the 3 and 1s and 2s I pass the other side to the equation, so 10 minus 4, 6, and make a vector b. set of characters, we use the pseudo inverse of A and make the dot product with A inverse. So if we run that, we have the solution here that and we replace the numbers we have that this set of answer is correct.
Okay, so to finish the TA, I'll explain what the pseudo inverse is, and we'll finish with that. Yes, please. Okay, so the code there that he used, the pseudo inverse, is a matrix that solves this problem. That, as you already have seen in class, this is the least square problem. And basically how do you get the pseudo inverse is that this function here is f of x, and to minimize this function you do the gradient of f, and to do the gradient of matrices and vectors you'll need a little bit of knowledge, but basically the gradient of this is equals to this right here, where here you have the transpose. This is the plus sign is different. And basically what you want is that your gradient is equal to 0. Why? Because if you have a vector, an axis here, and you have a function, for example this one, that is our f of x, the minimum here is when the gradient or the derivative is equal to 0, for those who didn't know. And now you only need to multiply and you get sorry for putting the letters a little bit diagonal, but if you apply the inverse of this matrix, you get finally that okay. And this term here is called the pseudo inverse. So basically what he did with the function pinv is calculate the pseudo inverse of this matrix A, and then by using the add symbol he multiplied, and this is a solution. Note that probably that problem had infinite solutions. This is the one with that satisfies this function. You could also find another solution if you change the objective function. If you change this function, you'll get another solution, but this one is the one when you do the least square objective function. And obviously what you get is the correct numbers, and the correct numbers were very easy to get. You already have a 1 3 3 1 2 1 3 1 3, and the first one, well, this one should be a 4, this one a 2, this one a 4, this one a 2 4 2 4. So your vector x, or the solution, should have been 2 4 4 2 4 4 2. Is that correct? You got that vector? Benjamin? Yeah? You got the same vector I just wrote. Perfect. I also have another activity, but that's for you later. And it's a problem similar to this one, but about the magic square problem. Well, any doubts about this procedure and how to model a system, a linear system? Or was this activity helpful for you to understand? Yes, everything's clear? Or you are already tired and want a coffee and a bread? Yeah? Okay, yeah. Let's finish the TA here. And this is already uploaded in YouTube. I'll put the link in the course website. Thank you all for being here, and I'll stop the streaming, but if you want, you can stay here and ask me something in Spanish.